Could black holes be the key to a quantum theory of gravity, a deeper theory of how reality, of how space and time works? Because we have a place called the event horizon, where we think that we have full control of the physics. We understand what's happening, but there is a fundamental clash between our two basic theories of nature.
Recent findings from the Dark Energy Survey, DES, and the Dark Energy Spectroscopic Instrument, DESI, are raising an unexpected possibility. The expansion of the universe may not continue forever. Cornell physicist Henry Tai has explored new dark energy models suggesting the cosmos might eventually slow, stop expanding, and collapse in a big crunch. If these ideas hold up, they challenge one of modern cosmology's most durable assumptions, that expansion is eternal. In this video, we'll examine the evidence behind this prediction, how it reshapes our view of dark energy, and what upcoming observations might reveal. Let's begin. For more than 20 years, the LCDM model has described the universe with remarkable accuracy. It assumes a positive cosmological constant, L, representing a fixed vacuum energy that causes space to expand at an accelerating rate. But new analyses combining DES and DESI galaxy maps with results from the Planck satellite have prompted scientists to re-evaluate this picture. These surveys chart millions of galaxies, measure large-scale distances, and track how the Hubble rate has changed over billions of years. When all data sets are compared, a subtle anomaly appears. The best-fit solution works slightly better if the cosmological constant is negative rather than positive. Intrigued by this, Henry Tai revisited the cosmological equations. His calculations indicate that a small negative L would let the universe expand for billions more years, but would eventually cause the expansion to stall and reverse. In this scenario, dark energy is still tied to the fabric of space, yet its influence slowly diminishes. Tai estimates that although the universe is currently 13.8 billion years old, it may be roughly at the midpoint of a 33 billion-year cosmic life cycle. Expansion would continue for another 11 billion years, reach a maximum size, and then gradually contract, starting about 20 billion years from now, until everything collapses in a final big crunch, a cosmic mirror of the Big Bang. Tai's paper, published in the Journal of Cosmology and Astroparticle Physics, doesn't claim this outcome is guaranteed, only that present data allow for a negative cosmological constant. If confirmed, it would overturn a foundational assumption of modern cosmology and imply that today's acceleration is only temporary. A negative L would dramatically reshape the theoretical framework that cosmologists use. Standard LCDM rests on the idea of a positive vacuum energy that pushes space outward forever. But if L is negative, or evolves over time, the universe would eventually contract. Tai and collaborators link this behavior to ideas from particle physics and string theory, where vacuum energy can naturally vary. Their model introduces an ultralight axion-like field, a particle that once behaved like a cosmological constant, but has slowly evolved since the early universe. As this field changes, it reduces the vacuum energy density, effectively flipping L to negative. This approach bridges cosmology with quantum field theory by replacing the notion of a static dark energy component with a physical mechanism, a changing vacuum. A dynamic dark energy field could also help ease the long-standing Hubble tension, the mismatch between expansion rates measured locally and inferred from the early universe. If dark energy has weakened with time, it slightly modifies both early and late universe measurements, nudging them closer together. Negative vacuum energy isn't a new idea. Versions of quantum gravity and string theory models already include anti-de Sitter universes with negative L. What's new is Tai's claim that current observations may actually be more consistent with such a universe. Many cosmologists remain skeptical, suggesting the deviation could be statistical noise or unresolved systematics. Still, the possibility of dynamic or negative dark energy is scientifically valuable because it is testable with larger surveys and more refined analysis. Researchers will determine whether this reflects a real physical process or just an artifact of the data. Regardless, the conversation is changing how scientists interpret dark energy, no longer a fixed constant, but something that might evolve, or even reverse, over cosmic time. If the cosmological constant is truly negative, the universe's ultimate fate changes in dramatic ways. In the traditional picture with positive L, expansion goes on forever. Galaxies drift into isolation, stars burn out, and the cosmos ends in a cold, dark, big freeze. In Ty's negative L model, the opposite happens. As dark energy weakens, gravitational attraction slowly reasserts itself. Expansion decelerates until it stops entirely. Then, contraction begins. Over billions of years, galaxies would approach each other, and the cosmic microwave background, now steadily cooling, would begin to warm as space compresses. Eventually, all matter, radiation, and space-time itself would collapse into an increasingly dense region until everything converges into a single final point, the Big Crunch. The timescales are enormous and pose no threat to the present-day universe, but they require cosmologists to rethink nearly every parameter we use to describe the universe, its age, curvature, and entire expansion history. The next decade will be critical for determining whether dark energy is truly constant. New observatories are already collecting the data needed to test these predictions. The Vera Rubin Observatory will soon launch its legacy survey of space and time, mapping billions of galaxies to track changes in cosmic expansion. ESA's Euclid mission is measuring the large-scale geometry of the cosmos, providing another probe of dark energy behavior. NASA's S-SPHEREX mission, along with future DSI observations, will deliver high-precision spectra that refine how we measure the Hubble rate. Together, these instruments will reveal whether dark energy is fixed, evolving, or trending negative. For theorists, the implications reach far beyond cosmic fate. A negative cosmological constant implies that the vacuum itself is not stable. Its energy density slowly shifts with time. That would link the largest cosmic structures with the smallest quantum fields, uniting cosmology and particle physics in ways never before tested. In that sense, the Big Crunch is more than a distant end. It becomes a tool for understanding how the universe operates on every scale. Dark energy may not be a constant after all. It might be gradually weakening, setting the stage for a future cosmic contraction. For now, the universe continues to expand, but the clues to its ultimate fate may already be written into the vacuum of space. We'll move closer to understanding how the cosmos will truly end. Thanks for watching, and keep exploring the universe.